Hello and welcome to section 1.4 on rates of change. In this section, we will discuss averages, specifically average rates of change, average velocity, and secant lines. Wait a second, what is a secant line and how is it connected to averages? Given a function f of x, a secant line to f is a line passing through 2 points on the graph. As a line is fixed, once 2 points on it are specified, there is only one secant line for every 2 points a f of a and b f of b on a function. What is the slope of a secant line? As the secant line passes through the points a f of a and b f of b, we can calculate the slope as rise over run. The slope equation for a secant line is known as an average rate of change. A rate of change is a measure of how input changes affect output changes. Take, for example, the function y equals x squared. Say we were interested in finding the average rate of change between x equals -1 and x equals 2. We would use our equation for average rate of change, letting a be -1 and b be 2. As f of 2 is 4 and f of -1 is 1, we find that the average rate of change is 1. Keep in mind, the slope of the secant line is the average rate of change, so we can find the equation of the secant line using the point-slope formula. We've now connected secant lines to an average, but why does the word average appear in average rate of change? We can best answer this question with an example. Suppose s represents the height of a ball in feet once it has been launched at time t equals 0. And suppose the function s has input t, which is measured in seconds, and outputs s of t, which is measured in feet. Let's calculate the ball height 0, 1, and 2 seconds after it has been thrown. Plug the t values into s, and we find that at 0 seconds the ball has a height of 0 feet, at 1 second, 64 feet, and at 2 seconds, 96 feet. The average rate of change for s between times 1 and 2 is 32. This number represents the average change in feet which the ball moves over 1 second. And if we calculate the average rate of change for s between times 0 and 2, we obtain 43. 43 what? 43 feet per second. The average change in feet per second over those 2 seconds. Notice that the ball only moves 96 feet in the first 2 seconds, 32 of which happen after the midway point. The velocity of the ball is not constant, so we are reporting the average velocity of the ball, not the velocity instant to instant. The same is true for general functions. The average rate of change records what it says, the average change in y per x unit over a certain x interval. Let's set some notation which we will use throughout the semester. We will reserve s for a function which represents an object's position with respect to time t. The units for s are distance measurements like feet, meters, and miles. When we find the average rate of change for the distance function s between times a and b, we are dividing distance by time. These rates of change have units distance per time, commonly known as velocity. The average rate of change for a distance function s is called the average velocity, and we will reserve the letter v for velocity. Take note, the average rate of change may resemble the slope equation of a line. It is the slope of a secant line after all, but you must not confuse the slope of a line, which is a fixed constant, and rates of change on a function, which may change with the values a and b. Challenge yourself. Pause the video and find the average rate of change for f and g on the intervals -1 to 1 and 0 to 2. Let's start with f, the line. Using our equation for average rate of change, and replacing, in the first case, b with 1 and a with -1, and in the second case, b with 2 and a with 0, we calculate an average rate of change of 1 in both instances. This should make sense, as slope is a rate of change, and what characterizes a line is constant slope. Turning to part 1 of g, we use the equation for average rate of change, with 1 replacing b and -1 replacing a. We then plug 1 and -1 into x cubed to calculate a rate of change of 1. A similar calculation in part 2, with 2 replacing b and 0 replacing a, we calculate an average rate of change of 4. Notice x cubed does not have a constant rate of change, a fact which can be visualized through secant lines. The red line has slope 4 and is the secant line for points 0 and 2, while the black line has slope 1 and is the secant for points -1 and 1. To sum up 1.4, we are working with averages. Remember that the slope of a secant line is an average rate of change, and that average velocity is a special case of average rate of change. Now that you know the basics, be sure to strengthen your understanding through practice.